Okay, so this next key that I'm going to do is for quiz 4. This is still on electrophilic aromatic substitutions, just a little bit more in depth. So the first question is predict all the products of this reaction. So bromine with SO3 and H2SO4. So when I look at this product, immediately when I see this, I know there's going to be some kind of substitution reaction. And I think even the question said predict all the products. So I see that there's an aromatic ring. So the only reaction that we really learned on aromatic rings so far are electrophilic aromatic substitution. And then this is just me getting my bearings. So first I see that. And then the next thing I'm looking at here is there's already a substitution on the ring. So because there's already a substitution on the ring, that means I have to think about directing effects. Like, is this going to go ortho, meta, or para? So when I look at bromine and I'm trying to decide, is this going to do ortho, meta, or para? I look at two things. I look at resonance and induction. And the bromine here, first we'll check for resonance structure. So if I attack an electrophile, any electrophile, literally doesn't matter what electrophile, the bromine would have a positive right here and the electrophile would add here. So the question is there a resonance structure that can stabilize that? This is so satisfying. Is there a resonance structure that can stabilize that positive charge? And in fact, there is, because the bromine can donate a lone pair. You can't see because of my word induction, but the bromine can donate a lone pair to make a resonance structure that looks like this. And the positive charge is on the bromine. Now, the bromine doesn't love that, but it's better than just the positive charge only being in one place. So there is a potential for resonance, and through resonance, it's typically going to direct your substituents to ortho-para, because it adds at the ortho position, the positive charge ends up right here, and you get a resonance structure. If it added at the meta position, the positive charge would skip over. There wouldn't end up being a positive charge right on the bromine. It would go here, here, and here. So when I see resonance at that position right here, that automatically makes me think ortho-para directing. And then for induction, typically if it's a strong electronegative group, it's withdrawing, and the electron withdrawing groups are usually meta-directing. So halogens are kind of weird because this does have a strong electronegative effect. So you would think it would be meta-directing, but resonance always beats out induction. So in this case, we have a resonance structure. So this halogen is going to be ortho-para directing. So that means that it could add our electrophile either ortho to the existing group, or it could add it para. Ortho or para. It just won't go to the meta position. So that's what I was looking for you to know for this question. Specifically, though, you couldn't just write electrophile. I wanted you to know that these reagents make HSO3 as the electrophile that adds. So SO3H. And I didn't make you know the mechanism for that, though, because SO3H. I didn't make you know the mechanism for that because the formation of this electrophile is pretty complex. So you did not have to draw the mechanism. You just had to know where the electrophile would add and why. Okay, so how do I get back to where? Here we go. So now let's talk about part 2. Okay, so that's the first part. Part 2 gave you this structure and asked, is this activating or deactivating? So again, we're looking at those two things, resonance and induction, and resonance typically is better than induction. So resonance or induction. So when I look at this molecule, if I were to add an electrophile, let's add it at the ortho position and get a positive charge right here. In fact, it does have a resonance structure that can, let's see, will I be able to, there we go, that can stabilize that positive charge. That would look like this. So because it has a lone pair there that has a resonance structure that gives you this, it's able to donate electron density to the ring, is what we say. So because it can donate electron density to the ring, we would typically call that activating. Because if it has more electron density around the ring, then it's more willing to attack and form this structure in the first place. So because there's this lone pair here, I know it can do this resonance structure. And even if we did it before looking at the electrophile adding, it could add right here and then this bond break and show you like, oh, there's more electron density right here. So then if there's more electron density right there, that would be a position likely to attack. So this lone pair right here adds electron density to the ring, so that makes it more likely to attack. So we say that it's activating it towards this electrophilic aromatic substitution. And also with resonance and activation, along with that goes orthopara directing. So we talked about that already just up above, is that if there's a lone pair, it stabilizes this position because the positive charge ends up right on the substituent, that's substituted in. The same thing would happen if it's substituted here. So either ortho or para will get you that substitution. Now meta, it makes the positive charge skip. So meta is better if this group is just electron withdrawing. And it does that through resonance, which we already talked about, not through induction, because induction is sort of about the polarity of the bonds and between carbon and oxygen. Oxygen's more electronegative, so that through induction is taking away some electron density. So hopefully that answers that question. Question 3 is for the following reaction. For the following reaction, what order will these reagents add? And we had a very similar question to this on your recitation packet, but there is a lot of things to consider here, and that's actually why I gave you the reagents, so you just had to think about the order and not what reagents were required. But hopefully, I guess when I look at this question, I'm first thinking this does nitration. This is a reduction reaction that eliminates acyl groups. So it basically reduces that carbonyl. And then this is a Friedel-Crafts acylation. And I did write acyl chloride here for you in case you didn't know the structure of this. But hopefully that condensed formula is something that you're more comfortable with by this stage in ochem 2. So this is a Friedel-Crafts acylation. So when I look at all these, I know this would add NO2. This would turn a carbonyl into just a plain carbon chain. And this would substitute a hydrogen on an aromatic ring for this group right here. So these are the things I'm getting from these different reagents. So that's the first thing, that you just need to know what each of these reagents will do. And then I think about, okay, now what order am I going to add them in? How does that matter? Well, if we just start with nitration, we know that the first thing you add on a benzene ring, it really doesn't matter. I'm going to switch pens because this one's running low on ink. It really doesn't matter where you add it because they're all the same. So the first step, we're adding our nitro, and it doesn't really matter where, because In a benzene ring, if you start with just a plain benzene ring, anywhere you add it will end up the same. But I know that this is deactivating because that nitro is actually positive if you draw the structure out. It looks like this, O minus and N plus. So the N is positively charged. So it's pulling electron density away from it really strongly. But also this is strongly electronegative. So both through resonance and through induction, I think. Is it through resonance? Can a resonance structure move here? Yeah. This bond could move over and it'd be positive here. But then that nitrogen would have, oh yeah, and then this would break up here. That's what would happen. Okay. So what was I saying? Anyway, so this is deactivating at the very least through induction. And that means that it's meta directing. You would rather go to the meta side than the ortho pair, a meta position than ortho para. So it's going to direct here. So that's good information because what we have here is our substituents are meta. So this is an option for me. The other things that it would make would be the acyl chloride. The AlCl3 will give me this. This has a partial positive charge right here because there's a resonance structure where that goes up. Looks like this. O minus. This is positively charged. So this is deactivating. Let me see if I move this up here, then I think, yes, this is deactivating through resonance and induction because we could have this double bond here and this minus and the positive B down here. So this is deactivating through resonance and induction. It's less deactivating than this because it's a partially positive, whereas this is fully positive. So because of that, this is deactivating through induction and resonance as well. This one is resonance too. So both of these are deactivating through induction and resonance, but this one, the impact is slightly less than it was here. So if my option are between, this one also is meta-directing because it's deactivating. So I could start with either the nitro or the acyl and get meta. If I had to pick between the two, I personally would pick the acyl coming first because it's has slightly less of an impact, but either one of these would work. So if you either started with nitro and then did this reaction, you would get worse yield. It doesn't work very effectively. So I would start with the AlCl3 and this carbonyl, and I would get this this structure. And then the next thing I would do would be my HNO3 and my H2SO4. And then I would have my this group, and I would have my nitro, and they would be meta. Now, that's not what I have up here, though. The acyl has gone away, and it's become this carbon chain. These carbon chains are electron donating through induction. There's no resonance structure, but they're not electron withdrawing. There's no electron density difference here. So these are orthopara directing. And so I didn't want to get this because it was orthopara directing until I had both my substituents on. And I definitely couldn't get this until I had at least added this, because what that reaction does is take my acyl group to a plain carbon chain. So now that I have both of my substituents and they're meta to one another, I'm running out of room, but I could use these reagents and basically eliminate this structure right here. And that would get me to my final answer that I'm looking for. So you the answer I said was the most correct is to use C first, and then A, and then very last B. However, I gave credit if you did A first and then C, because it would probably still work some. It just wouldn't be great. And then B last. But you absolutely got no credit if you're, or maybe like just one, I don't know. If your zinc mercury reduction, if this reduction happened before you added the acyl group, that wouldn't work. And I had a very similar question to this on the exam where the same thing was true, where you have to add your, you have to get rid of your carbonyl after you've added your carbonyl. So you could eliminate a lot of questions on the exam by just making sure that this came after this. So that's how I would approach that question. And then the very last question is, why won't the reaction given proceed this the way that it's written? Indicate why and what the correct answer would be. Okay, so the reaction given is a Friedel-Crafts alkylation. And this is just another electrophilic aromatic substitution. And the first step that happens here is our electrophile is formed via carbocation. So this leaves and this attacks, just like we saw in quiz 3 with the Friedel-Crafts acylation, and it gives us our electrophile that looks like this. And so for the reaction to proceed this way, then the benzene would have to attack right here. But anytime you see a carbocation, I hope that a little red flag waves in your mind and you stop and say, carbocation rearrangement, because that is the biggest thing. If there's ever a carbocation as an intermediate, there's the potential for rearrangement to happen. And so a rearrangement happens in the form of either a hydride shift or a methyl shift. So either a hydrogen nearby or a methyl nearby can trade places with a carbocation to make it more stable. So right here, this is a secondary carbocation. I guess let me say that allylic or benzylic, basically carbocations stabilized by resonance, are usually going to be ideal. They're roughly equivalent to tertiary, but if you have tertiary and allylic or benzylic, that's the best carbocations. And then we would have secondary, and then primary is the worst. So this is a secondary, but there's a tertiary position right next door. And there is a hydrogen there that can trade places. So essentially these electrons just shift over, and you end up getting your, this is a 5-membered ring, your carbocation moving here. And now there's 2 hydrogens here. One of the hydrogens from here shifted over to here. So that we could get the most energetically favorable thing, which looks like this. So if this is our carbocation that the benzene attacks, the bond forms right there, and your final structure looks like your benzene with a bond formed to right here, but also at that position is an ethyl group, and then your 5-membered ring. So it looks like that. What we have here is your benzene formed a bond to right here before rearrangement. So this reaction won't proceed because the electrophile undergoes rearrangement, and this would be the final correct product. Okay, I hope that was helpful to you. Let me know if you have any questions. Good luck studying.